Now for the chapter 8 or part 8, we're going to talk about the one-way slab, where this one-way slab is a very important topic because this is the basics of how to design a slab, and then the following one will be the two-way slab. Now, generally speaking, reinforced concrete slab, they're used and the methodology of designing the slab is used in all the floors and roofing of the buildings, the bridge decks, the building walls, tank walls, and retaining walls. Those are the same methodology, how we design a slab or how we apply the load to the slab and evaluate its stresses. Pretty much is the same as we look at walls when we're looking at the out of plane direction of the wall. So whenever you're looking at a wall in this direction, it's like you're looking at a slab. Same exact design, but not necessarily same exact specifications. The supports of the slab are RC beams or steel beams, masonry or concrete walls, columns, ground or slab on grade that is sitting on the ground right away. So now it doesn't really span much, but it takes a lot of the pressure and distributes it to the soil. One-way slab or a concrete structural floor panel for which the load is transferred primarily in one direction, which means there will be not the chance to do this. This will not happen. The reason why it's not going to happen is one of two things. Either I don't have supports in these directions or in these sides, or the length aspect ratio to the width is too big. And they specified it to be about 2. So if you see a 2 or more aspect ratio, then you define it as a one-way slab. Normally when we're talking about this ratio, we're talking about the clear span length. But from simplicity, a lot of times we just take it as the center lines of the beams because it won't make much of a difference at the end. Remember that not only the aspect ratio plays a vital role in determining the one-way slab, or whether or not it's a one-way slab. If I have the short directions containing supports and the long directions with no supports, then the force or the stresses will be forced to go in the direction where the supports are. So in this case, the one-way slab, this is also considered a one-way slab, but it goes in the long direction, not in the short direction. And then this one is, as we know, is also forced to do this. And note that the load path following or followed the beam locations as and was not dictated by the span length. Slabs are usually horizontal, right? When we're talking about stairs, those are also slabs, types of slabs, but they're inclined. Of consistent thickness, it's very rarely that you find different thicknesses in slabs. Square or rectangle, continuous over several supports. As much as we can, we try to enforce this continuity above different supports, which means I try as much as I can to do this, to be able to reduce the stresses. So the more negative moment I have, the less positive moment it will end up having. One-way slabs are designed as rectangular beams with a beam width equals 1. How does that happen? Or where do I get the width equals 1 or unit width? It comes from looking at the slab that is spanning at several spans like this, right? And instead of designing the whole thing, I just take 1 meter wide strip, which is this strip. So I look at the span and I take only one strip, and that one strip is 1 meter wide, or 1 unit, or whatever the units that you're using are. I take 1 unit and I run it through. So everything in here will be represented on that 1 unit because we are dealing with uniform load. So that in the design we're dealing with what we call the uniform load. Now we take that one strip just like this, right? And we put all the loads of that 1 meter on that strip. We design it. And then when we design it, how does it look like? It would look like this. Exactly like a beam with a thickness equals to the slab thickness, T slab. And with a width equals to B equals 1 meter. And then start designing this. I either put the reinforcement at the bottom when it's a positive moment, or I put it at the top when it's a negative moment, and so forth. So I take that 1 meter width strip through the direction of loading. So I know that the direction of loading going this way, then I take the strip in the same direction of loading, I apply the loads, I figure out where my supports are, I place them to get my free body diagram, and then solve this free body diagram to obtain all the moments that I need to design for. Now those would be MU. Okay? Now the loads on the slabs are normally uniform loads. They're sometimes are heavy concentrated loads. We either thicken the slab in these areas, or we provide a beam that takes that concentrated load if possible. Usually stirrups are not needed because the shear provided by the slab is enough to take all the applied shear on it. Now the reinforcement, if we're looking at this slab here, reinforcement of a slab, if I'm looking this way, there will be two types of reinforcement. The first one will be the one going this way. And then the second one will be the one going this way, on top of it. Right? So I have two reinforcements here. One in the short direction, I will consider this was the short. Sorry, I'll use the blue color. Here, if this here is the short direction, and that one here was the long direction. Right? Remember, we're talking now up to this point, we're talking about one-way slab, right? So in this case, which one would be my main and which one would be my secondary steel? My main will be the blue one, main reinforcement, because it is going in the short direction. And my secondary would be the black one, secondary reinforcement. Is there a difference between them? Yes. We have some differences that we will consider in terms of distances, maximum distances, in terms of how to calculate them, and so forth. But to know where my main reinforcement is, I need to figure out where is the short direction first. So if I'm looking here, my main reinforcement will be the reinforcement going, we use the blue, let's use the blue again. My main reinforcement would be the reinforcement going this way. My secondary reinforcement would be the reinforcement going this way. Clear? So this would be secondary, and that guy here would be main reinforcement. Clear? Very simple. Where the direction of the loading is, where the short direction is where I place my main reinforcement. Okay, thinking about the behavior of a one-way slab, deformed surfaces are or is almost cylindrical. So as if this is part of a cylinder, right? You know what a cylinder is? Like this. And the load is transferred in one direction only. And we consider a 1 meter wide strip. This is the 1 meter wide strip. The curvature in the short direction, L short, considering this is L short, is much more than the curvature in the long direction. So that means it curves more in the short direction than in the long direction. If I take a strip in that direction, I will barely see any curvature. Why? Because the load is predominantly going in the short direction. Much higher moment in the short direction and main steel in the short direction. Design is similar to a beam design, exactly like a beam, but I know that B equals 1,000 millimeters, right? And then H equals the thickness of the slab. Now going to the behavior of the two-way slab, it would be curved in both directions. So I have a deformation surface that looks like a dish, not like a cylinder. So it deforms in both directions. Load is transferred in two directions. Considering 1 meter wide strip curvature in the short direction is more than in the long direction, but I still have curvature. And then more moment in the short direction, main steel in both short and long direction. But most probably the short direction takes higher moments. Why? Because it is the stiffer direction. So let's think about this. If we have something that is interconnected like a slab in the two directions, right? Now consider those are my two strips, the long strip and the short strip. This is part of a slab. If my slab was like this, right? And then what happened is I placed some load here. Now both of them will be deforming exactly the same deformation because it is the same slab, right? So I will end up with the short direction deforming delta, if we call it delta. Right? And then the long direction also deforming delta. Delta here and there is exactly the same, right? Both deltas are the same. Let's get to the stiffness equation. What does the stiffness equation say? The stiffness equals the force divided by deformation, right? Now, which one is more stiff? If I say this one K1 stiffness, this one K2, which one has higher stiffness? The short one has higher stiffness. So K1 is higher than K2. K2 is the less stiffness. The longer the beam, the less stiffness it has, right? And then if we put this on one side, so delta equals F over K, right? In this case, I would put the two F's and the two K's to equate them. So I have F over K. That means F1 K1, F2 K2, right? So how much force I have? If K1 is the higher one and K2 is the lower one, to have them equal, because they have the same distance, the same displacement, my F1 will have to be higher than F2, right? To keep the same ratio. In other words, the stronger guy, because they are forced to have the same deformation, mathematically speaking, if we're putting it back to the stiffness, this is my stiffness, because they have higher stiffness, the short direction has higher stiffness, it will be forced to take higher force. You got the idea? Now, if both directions are the same, then they take the same forces. Now, those forces will be translated into moments, shears, and stresses, right? Generally speaking. Reinforcement in the one-way slabs. We have in the short direction, we will use moment. So in the short direction, I have some moment. That moment will give me some area steel required. Area steel required. I need to compare this area steel required with area steel minimum and take the larger of them. So this is my main reinforcement. My main reinforcement will be the larger of needed steel and minimum steel. This is required coming from rho required equation, the same equation we had before. And then in the long direction, we will not have required steel because it does not have moments, it does not have forces. So we only use area steel minimum. So this one is area steel minimum. So the short is the larger of area steel required and area steel minimum. Okay, we take maximum of them. In the long direction, it takes only the area steel minimum. What is the minimum steel in slab, or where does it come from? It comes from the temperature and shrinkage requirements. What normally happens in slabs, because they're long, big surfaces, is that they end up cracking because of temperature changes, heat of hydration, and shrinkage during the early age of the concrete. So what happened is, the code tells you you have a minimum area steel that you need to abide by. What are those minimum? It is depending on the F yield. If it's larger than or equal to 420 megapascal, you take the greater of 0.0014 area gross, or 0.0018 times 420 over F yield area gross. What is area gross? I'm going to look at the steel in its section. This is my steel here, right? So if I'm considering a 1 meter wide times some H, let's say that this H was 200 millimeters, right? Then my area gross equals 1,000 times 200. That's in millimeter, that's in millimeter. Okay? And then I calculate how much steel area will be needed here as a minimum steel. So the amount of steel that you place in your section, if the minimum amount of steel depends on how much area you have. Okay? And then, of course, if this goes up to 200, you will probably need to put another layer up on top. You cannot have one layer for a 200 millimeter slab. That's too thick. And then distribute your area minimum among the upper and lower steel. How about the maximum spacing between my bars? Those are my bars. Center to center of the bar should not be bigger than, if I'm going in the short direction, if this here was my short direction, then that distance is the larger of 3H or 450. What is H? The full height of the slab. If I'm going in the long direction, now those bars here, the distance between them, this here is the long, should not be larger than 5H or 450. Very simple equations, all will be given to you to be able to distribute your reinforcement. Again, the distance between the bars depends on the direction. Either 3H or 450 or 5H and 550 and 450. Now finding the steel, once I find that I need an area steel, a certain area steel, if I got here from my moment, I got some AS and I want to start distributing this AS. How do I distribute it? Like very simply, I can go to the table and, for example, I say, I'm going to take S equals 200. If S is 200, that means N equals 5. Where did this come from? 1,000 divided by 5, or divided by 200, that gave me 5 bars. So I find the proper bar designation to have 5 of them to satisfy my AS. This is one way to go. Again, I'm looking at a certain AS. I will assume a certain spacing. Another one will assume spacing equal 150 and then find N. What is N? 1,000 divided by 150. Right? And so forth. Now, this is one way to do it. The other way is to find area of the bar, to put this equation, and from the cross-sectional area of the bar, find your spacing. So I'm flipping. I say I will try phi 10, then I put here, for example, 71 millimeters square. Area of phi 10, right? And then solve. Now this was found from my analysis. Solve to find S, and then round my S down, right? Normally we go every 5 centimeters, 50 millimeters. Okay? Try to be as consistent as possible in your drawings, because people who will place the reinforcement might make mistakes if you keep changing it. So it's better to keep consistency in your specifications on the drawings. Bar diameters that are usually used are the ones between 10 and 20 millimeters. That's for slabs. And the spacing is normally between 7.5 millimeters all the way to 300 millimeters. Definitely we don't go beyond the 450 or the 5H or the 3H. Now the example here says that a one-way slab RC slab carries a uniformly distributed surface load equals 6 kilonewton per meter squared. I have a 6 kilonewton per meter squared surface load as a life load, right? This is life load. And the slab also supports a wall at the end of the cantilever, this wall. And the weight of the wall is 15 kilonewton per meter. It's already given as a line load. Now the concrete is to be used normal weight concrete with a compressive strength F prime C 21, the yield strength F yield 420, and suggestion is to use number 13 bar. Where is the direction of my strip? It will be in the direction of my force, and the direction of the force is a short direction. Where is the force going? This way. Right. So this way I will take a 1 meter wide strip this way. Right. In this case I have a support here, and I have another support here and a cantilever. So how it looks like, it will look something like this. Now it has its own self weight, that's the dead load. It will have some life load as well, and it will have a concentrated load out on top here, which is the wall load. So this here is dead, that here is life, and this guy here is also dead, which is the wall. Clear? And then I go with the answer. Let's look here. The first step, now I know the free body diagram looks like this, right? Now how do I determine the dead load? Number one is to select the slab thickness. How do I select the slab thickness? Based on the limits set by ACI, I can go and check cantilever or simply supported or one-way continuous or both end continuous. For a 1 meter strip wide, draw the shear force and bending moment diagram, design the steel, and then design the secondary steel, shrinkage and temperature, and then sketch the final reinforcement. To determine my slab thickness, I go to Chapter 7 in ACI for a one-way slab. And it tells me that I have for the simply supported one end, both end, and a cantilever. This here is which case of them? I have two cases. This case is the cantilever case. That case here is one end continuous, because it has continuity from one side. Then in this case, I will have to compare those two numbers. L over 24, but in this case it will be this L, L1. So this one, L1 over 24, will give me a number. And then I will have to compare it to L2 over 10. So I have two numbers to compare, because the cantilever length is different than the span length. So in this case, I have 4 divided by 24 gives me about 16.7 centimeters. 1.5 divided by 10, that gives me 0.15. Which one do I choose or go with? Definitely this one. Now, the way I round slabs is I go every 20 millimeters, which means I have the 10, 12, 14, 16, 18, 20, and so forth. Practically speaking, this is how they do it. Sometimes they have a 15 centimeter slabs. That's possible as well. But if you're given the chance, just go with the 2 centimeters folds. Okay, so that means I have a 16.7 centimeter. I choose 18 centimeter slab, 180 millimeters. Now it's easy to calculate my dead load. So I'm going to calculate my dead load. It's going to be the 1 meter wide strip times the 0.18 meters times my gamma concrete. It gave me 4.32 kilonewton per meter. So every meter weighs 4.32 kilonewton. And then my life load was given as 6 in the 1 meter wide strip. That's the 6. And that gives me 6 kilonewton per meter. I then take the ultimate. I convert my service load into ultimate load. And that ultimate load ends up being 14.78 kilonewton per meter. Now, the dead load that was here was 15 kilonewton per meter. Since I'm using the 1.2, 1.6, I have to be consistent. So I multiplied by 1.2, and that gave me 18. Now I have my full factored or ultimate case free body diagram of my strip. In this case, I can very easily solve it. I can find my shear force diagram, bending moment diagram, right? I will require some main steel down here at the bottom and main steel up here at the top because the shape of the moment looks like this. So I have tension down here and I have tension up here. Which one is more critical to design for? Let's start with the 43.63 kilonewton meter. So now my moment, my ultimate moment is the 43. I find the R, very simple, same exact procedures, and then I find my rho required. The first step to find my R is to calculate my D. What is my D? In this case, I don't have any stirrups anymore. I just have the concrete cover. Normally, concrete cover for slabs is 20 millimeters. So in this case, my D will be equal to H minus 20, that's the concrete cover, minus the diameter of the bar over 2. So this would be my D. Okay? Now what's the diameter of the bar? Remember at the beginning of the example it says assume a phi 13. The exact diameter of phi 13 is 12.7 millimeters. And my H was given as 180 that we found in the last step. So now I found my D to be 153.7 millimeters. Remember one important thing. The D in the short direction will be different than the D in the long direction. Because in the long direction, I will place my bars above the short direction bars. So we will have a different calculation. But for now, let's continue working in the short direction. I find my R, I find my rho required equals 0.00521. And then my S, which is rho BD, will be equal to 801 for every meter. Remember this, my area steel is found per meter because I'm working per meter, right? So compare this to the AS minimum. AS minimum is 0.0018 BH. I got 324. Then my rho required controls. And then I can go to the slab and find the area steel, to the slab table and find the area steel right away. Or I can go with calculating the S from the equation we talked about, area bar, which is the phi 13 area bar. This is area by of phi 13 divided by 801 times 1000, which is the distance that gave 161. A 161 can be rounded down to maybe 150, right? But here I just take it as 160 and we'll explain the rounding in the next slides. Or we can go to the table A3 right away and choose phi 13 at 160 millimeters. Let's now check the S maximum because that's the S chosen. This is my S now. I have to compare this S to my S maximum. S maximum is the bigger of 3H and 450. Right? So it ended up 450. I chose 160. 160 is smaller. I'm good. And then my AS used is now going to change a little bit because we rounded down, remember? Now we chose the S smaller than the S we got, so it got to be 806. Use the 806 in your actual calculations to find A, C over D, phi mn, and then compare your phi mn to your mu, and if it's bigger, you're good. Simple? Simple. Here is the table A3 that we were talking about. And table A3 is specified for slabs. So if I have, for example, a phi 16 at 100, then I just take the phi 16 at 100, and then this is the number. This is my AS. So AS here would be 1990 millimeters square. We got the idea of this table. This table is very simple and very handy. It makes life very easy. So you don't really have to go with this SB or S equals AB over AS times 1000. You don't have to go with this. You can just directly use the table because the table goes every 10 centimeters or every 10 millimeters increments between the spacings. Now going for the positive moment. What was the positive moment? 11.77. This is the moment that was down here. Right? So now we're talking about still the main direction, but the bottom steel, not the top steel. What we solved in the last part was the top steel above the cantilever. Here we're going to solve for the bottom steel underneath the positive moment. Now, same idea, plug in mu in the equation of R, get R, plug it in the rho required. I got rho required equals 0.00134. And in this case, I can calculate my AS required to be 206. Remember what was AS minimum? 324. And in this case, AS minimum governs. So I have to use the minimum steel at that bottom side. So I take AS equals AS minimum using number 10 bars. Somebody else could use number 13 and stick to it. That's fine. And then in number 10 gave me the usage of distance equal 219. I can drop it down to 210. Check the AS maximum was 450. We're good. I keep going to the long direction. Long direction is always AS minimum. Always AS minimum, right? So in this case, I use the AS minimum, also the 219 spacing using number 10 bars. And then S maximum is 450, and then using the same is going to be there. So all the red ones are the number 10 at 220. The black one is the number 13 at 160. Is this practical? The answer is no, it's not practical. What's the practical side? Is to use every 5 centimeters increments. So I have at 200 and at 150. That's more practical and more used in the sites. Now, talking about the continuous beams, there was a alternate analysis method that we talked about, and we said we will explain this. It is a method that is introduced by ACI, approved by ACI to be used. Now, continuous beams and one-way slabs need to be analyzed to determine the internal shears and moments. They are structurally indeterminate as the number of unknowns exceed the number of equations. Computer software is needed, but alternatively, we can use the alternate analysis method. What is the alternate method? Before we start with the alternate method, we have to look at its limitations. If we don't have those satisfied, we cannot use it. What are those? Number one, it is 2 or more spans. Number two is the difference between each span and the next span is not more than 20% difference. So I don't have really long spans and really short spans. They have to be very close. Number three is uniformly distributed loads only. So I cannot use concentrated loads with this method. And life loads are not very high. They cannot exceed 3 times the dead load. And prismatic or constant section or cross sections, which means the cross sections don't change. Okay? Looking at this method, that's what ACI tells us. It tells us that those are the values for moments and shears, and we took the values and placed it in a much easier figure to see how they look like. This is how that looks like. In the shear, take the first one to be WL over 2. Which L? L1. And then the second one, 1.15 WL over 2. And then WL2 over 2, WL2 over 2 for all the remaining ones. So only the first one gets WL over 2 and an extra 15% in that shear. Good? That's for shear force diagram. Now for bending moment diagram, if I draw the moment, it will look like this. So I have WL over 11 in all the inside ones and WL over 16 in all the positive inside ones. Remember that this length is used for the positive. But the average of those two lengths is used in the negative. Make sense? I think it makes sense because the negative is sharing between two spans. So the average here gives this. But the first one, the first span, has 3 different values. WL squared over 24, WL squared over 14, and WL squared over 10. A little bit different, and we can discuss the difference. That's if you have the final one as a spandrel beam, if it's a beam, if this was just a beam. Now, what if it's a column? If it's a column, then the difference would be that you have here a WL squared over 16 instead of 24, and then 14, 10, 16, 11 as you go. So the same thing applies, only the difference comes in the first moment. That's it for this chapter. I hope everything is clear.